Okay, we'll go ahead and get started. Can the people on Zoom see the slides and hear me okay?
Yes.
Thank you. So need to take attendance again today. So I'm going to go ahead and call your name. If you're present, please speak up. Carolyn Ahe.
Here.
Bailey Barber. Matthew Cathro. Scott Detweiler.
Here.
Evan Ellis.
Here.
Taylor Friend, I see there. Alex Hoke. Okay. Jalen Holdaway. Kaylin Kearney.
Here.
Bethany Lancaster.
Here.
Marissa Lanzati.
Here.
Mia Maddock.
Here.
Blake Miles.
Here.
Jalala Muhammad.
Here.
Irna Pilipovic.
Here.
Conrad's here. Jacob Schopper.
Here.
Jacob Schulstans. AJ is here, okay. And Marco's here, okay. So, once again, Jacob Schulstans, is he here? How about Jalen Holdaway? Okay. So what we're going to do today is we're going to continue on with chapter 11. I think we'll get finished today. And just a reminder, chapter 11 is what we're going to have a quiz on next Thursday. So Tuesday, we spent a lot of time talking about intermolecular forces and things like that. And hopefully you had a chance to kind of review some of the homework and you're a little more comfortable with that. And we spent a fair amount of time giving examples that centered around boiling point. These intermolecular forces, as we said in the very beginning, also impact some other physical properties. And those are melting point, viscosity, surface tension, and capillary action. And so what we're going to do today is we're going to talk about some of these other things, what they are, what they mean, and how those intermolecular forces impact things. Okay, so the first one let's talk about is viscosity. And the definition of viscosity is that it's the resistance of a liquid to flow. And so the example we have here on the slide are two types of motor oil. So if you ever see motor oil, they always have this SAE number 40, 10. Well, that's just a way of telling you the viscosity of the oil. So the lower the number, the lower the viscosity. And if it has low viscosity, it's less thick, it pours more quickly, more easily, things like that. So next time you see the motor oil thing, you'll have a feel for if it's SAE 40 or 30 or 10 or whatever, you know that lower number means that the oil is just a little less viscous, a little less thick. The example I gave the other day is syrup versus water. Syrup is pretty thick and pours pretty slowly. And so that would be more viscous than the water would be. And so what this viscosity is really telling us, it's related to the ease in which the molecules can move around each other, move past each other. So the more intermolecular forces you have, then the more viscous that the material is going to be. The other thing about viscosity is that it decreases with higher temperature. So I think we've all seen where you've had something, you know, the one I always think of is like shortening. You heat that up and now suddenly it gets less viscous and you can pour it and do some things, let it cool down, it solidifies again. And if we think about why that is, if we're trying to disrupt those intermolecular forces, you think you need to put energy in to kind of break those pseudo bonds. And we've talked a lot about energy. And usually when we're talking about energy, we're talking about heat, right? So here's another example of some hydrocarbons. So we have hexane, heptane, octane, nonane, decane. So in other words, straight chain alkanes. And then we have viscosity values. And what we see is we see that as we go from the smallest one to the biggest one, the viscosity is increasing, right? Because 10 to the minus third is a bigger number than 10 to the minus fourth. So it's increasing. That makes sense to us because remember we said one thing about those intermolecular forces. So here with these, do we have any hydrogen bonding going on? I see a 1 yes, 1 no. Do we have a tiebreaker? Will we have any hydrogen bonding with these? No, that's right. No, why not? Because we don't have that oxygen or that fluorine or that nitrogen that the hydrogen is bonded to. We have hydrogens, okay, but we don't have that electronegative atom, that electronegative element next to it to kind of do that electron shift. But remember we said on these, then that's where those weaker dispersion forces come into play. And we said that we get more intermolecular interactions, the bigger the molecule, right? Higher molecular weight means more interaction. If we have more interaction, then it's going to be kind of held together a little bit more. If it's held together a little bit more, it should be less viscous. And that's what we see in this series of alkanes right here. Okay, let's move on to surface tension. So surface tension is what you're talking about there is its definition is the energy required to increase the surface area of the liquid by a unit amount. So it's kind of a nebulous definition, at least in my mind. But really what you're talking about, and this kind of cartoon representation here on the right-hand side kind of explains it best, I think, is these are water molecules. And what you see, the water molecules that are in the bulk of the solution, they're having interactions. One of those molecules is having interactions all around it. When you get to the ones on top, they have interactions with the ones to the side and below. So it's kind of pulling it into the solution, but there's nothing pulling it out. So surface tension arises because there's no upward force to cancel the downward force. So the molecule feels like it's kind of being pulled down into the group, okay? And so what's really interesting about surface tension is what we visibly see when we think about surface tension. And so if we take water as an example, that inward force makes it almost like it kind of has a little bit of a skin to it, okay? So in other words, that's why the classic one is you'll see bugs kind of running across the water. That's a result of surface tension because the bugs are actually denser than the water. But because of that kind of tension and the bugs don't weigh very much, they're able to kind of skirt across it. The other thing that's a function of surface tension is when you see water beating up. So Some surfaces it beads up, other surfaces it soaks in. This gets down to a few things, but one of them is polarity. So if the surface is non-polar, water is very polar. So that interaction within the water is stronger than the interaction of the water with the surface. And so that's why it beads up. And that's all related to surface tension. The way you measure surface tension is there's several different ways, but one common way is something called a Dunois tensiometer. And literally what it is you have this circular wire ring that you lower down onto the water, you get it submerged a little bit, and then you pull it up, and the amount of energy or effort it takes to then break it, and the water will kind of come up with it to a point, and then it'll disengage. That's how you measure surface tension. And so surface tension is a big deal in terms of just some of the properties of things, but where it's really a big deal is something called interfacial surface tension. And that's where it's the surface tension between two different liquids. And that's a big deal in a lot of formulations. So a lot of commercial products, the formulators do things to get things that are polar and non-polar and normally don't want to get together. They'll use interfacial surface tension measurements to figure out ways to put additives in and make them cohesive. A lot of skincare products in that depend on kind of tricking surface tension to make things that aren't compatible be compatible. Somewhat related to that are cohesion and adhesion. So intermolecular forces that bind similar molecules to one another are cohesive forces. So you've got these molecules, their association with each other, those are called cohesive forces. Then the intermolecular forces that bind a substance to a surface, that's adhesive forces. So if you think about it, you've got these molecules and they've got these potential to have intermolecular forces, whether it be hydrogen bonding or whatever. And then the surfaces have a certain property. It's kind of like we just talked about with the beating of the water. If it's a real non-polar surface and water is real polar, you're not going to get much adhesion there. And so these two forces of cohesion and adhesion are what are involved in something called capillary action. Does anybody know what do we mean by capillary action? So have you ever seen a thermometer? And what is that? That solution goes up and down, right? With the ability to go up and down, because no one's pushing it, right? It has to be able to flow up and down without some force. That's a capillary action. So capillary action is the ability of liquids to rise up narrow tubes. And there's two forces at work here. Adhesive forces attract the liquid to the wall of the tube, and cohesive forces attract it to the liquid itself. Two things that you can look at. So on the left here in the figure, we see some water, and on the right, we see mercury. It's a little hard to see on the slide, but if you look closely, look at the meniscus on each of these. Water has a concave meniscus, and you probably remember this from lab. And concave means it kind of goes down, right? And so that's because water has a stronger attraction to the glass than it does to the other water molecules. So it kind of goes up the side a little bit more than the middle. Mercury is just the opposite. Mercury has a stronger attraction to the other mercury atoms, than it does the walls of the glass. And because of that, if you see mercury, and this is where you can kind of see it in thermometers, but it's actually kind of hard to see in that, but it has a convex meniscus. So in other words, if you look closely, it goes up in the middle and goes down a little bit on the sides where it's near the wall of the glass. The reason for that is, at least on the water, is if you look at this kind of molecule diagram we have on the slide here, the reds on the side of the glass here, glass is made of silica basically, and it has siloxane groups on it, which is Si with an OH. That hydrogen gets donated, so Si bonded to oxygen with a negative charge on the oxygen is real prevalent in glass. And so if you think about the water, remember we said in water, we had a hydrogen atom and 2 oxygen atoms. What did we say about kind of the charge distribution there? We said that from a polarizability, a dipole type perspective, that oxygen is going to have partial negative charge, right? And the hydrogen's partial positive. So you've got these water molecules, which is the little white balls on the water molecule. You have those partial positive charge on the hydrogen. It's looking for some electrons to associate with, right? Well, the glass wall, because of the siloxane groups, the SiO minus groups, it's a nice match. And that force, that interaction is stronger than the water within itself interaction. Mercury, you don't have any of that stuff, okay? You don't have anything that's really looking for that. So that explains why it doesn't have a greater affinity towards the glass tube. So that's the reason. So anyway, so that's the result of that. Like I said, capillary action is pretty important in a lot of things. A real simple one, like I said, is the thermometers. And then also next time you read a meniscus in lab, you'll understand why it goes down instead of up. So let's talk about phase changes a little bit. And so when we're talking about phase change, we're talking about taking a state of matter and converting it to another state. So in each of these, either energy is put into it or energy is given off by it. If we put energy into it, is that endothermic or exothermic? Endothermic, good. Endo, in. And so if energy is coming out, given off, it's exothermic. The phase changes we're talking about are melting, freezing, vaporizing, condensing, subliming, depositing. And so here we have an energy diagram of that. And so the ones in blue are endothermic processes. So in other words, energy had to go in to make that happen. And the ones in red are exothermic processes, which means energy was given off, was released for that process to occur. And so let's just take a look at these for a moment. So we see here, looking over on the left of the figure, we see this melting fusion type of process. So this melting process going from a solid to a liquid, that's endothermic. And you think about it, if you had something that was frozen and you wanted to thaw it out, you'd have to put energy in, right? You'd add some heat. Then if you have a liquid and want to go to gas, so in other words, vaporize it, once again, what would you do in normal life? You would put some energy in to make that liquid become a gas. So that also is an endothermic process. And then the last endothermic one, going from solid to gas, skipping that liquid phase, that's called sublimation. And so to sublime something, once again, you have to put energy in to have that physical phase transformation. Coming back the other way, if we have a gas and it gets condensed down to a liquid, then energy is going to be given off. If we have a liquid and we want to freeze it, we've got to remove energy from there. We've got to get energy out. So once again, that's an exothermic process to get it frozen. And then finally, if we went from gas down to solid, a deposition type of process, that's exothermic as well. So what we can do is we can do calculations to see if we're taking a material from solid to gas to liquid or back, to see how much energy would be required to make those transitions. And so can you think of any time where it might be useful to understand how to do these energy calculations? Anyone have any thoughts on that? People on Zoom can answer too. Well, the one that always comes to mind for me is cooking, okay? You think of when you're cooking things, that's almost always about energy transfer, right? And it's like, why do some things take longer to cook than others and stuff like that? Well, it gets down to some of those physical properties of whatever it is you're cooking. You know, if you have something that has really tight intermolecular forces and you're trying to get some of these transitions to occur, then it's going to take more energy. More energy probably means either higher temperatures or more time or something like that. So I don't claim to be much of a cook, but my younger daughter is, and she's a chemist also. And it's interesting to hear her talk about her cooking because she takes it from a chemistry perspective. And so it's kind of neat to hear that. But it's really, you know, it really is a case of that. So there are some terms that we want to know in order to do these calculations and think about energy changes associated with these physical changes. The first one is heat of fusion. And heat of fusion is defined as the energy required to change a solid at its melting point to a liquid. Okay, so you get to that melting point, whatever that temperature is, and then you have, once you get there, you have to convert the material from a solid into a liquid. And so heat of fusion is that energy value that's required to do that. The next one is heat of vaporization. And kind of similar to heat of fusion, in this case, it's the energy required to change a liquid at its boiling point to a gas. So once again, you get the liquid up to whatever its boiling point is. And then what's the energy it takes once you've reached that temperature to then convert it into the gas. And then finally, heat of sublimation, that's the energy required to change a solid directly to. So this goes back to those physical changes that we talked about in the previous slide. And so these are terms that if you're going to do some of these calculations, you'll need to have values for heat of fusion, Do you have a question? Okay, I'll go on then. Heat of vaporization and then heat of sublimation. So, okay, and that leads us to heating curves. And there's quite a bit of information on this, but this is really kind of like a graphical description of what goes on in terms of heat flow for these processes to occur. So if we graph temperature versus heat added, okay? So in the x-axis, we're adding more and more heat to whatever the molecule is. And then the y-axis is telling us what the resultant temperature is from that addition of the heat. And so within each phase, heat is the product of the specific heat, the sample mass, and the temperature change. Okay, so then the temperature of the substance does not rise during a phase change. And so what that means is if we start here at A, and this is water, so we have ice at minus 25 C, we add heat into it, right? And we see a temperature change. And we see the temperature kind of going up fairly quickly. That's a pretty steep slope on that line. But then when we get to 0 degrees C, which is the freezing point of water, we see that it stays here and we apply more heat. So we continue to add heat, but the temperature doesn't change. And the reason why is you don't get a temperature change until you've basically gotten all the molecules to that 0 degree temperature, okay? So you add heat, it gets to, in this case, the freezing point, melting point. Then you have to add enough heat to get all the material to that temperature. Once that occurs, which is point C on the plot, then as we add heat, we see once again it goes up, not quite as steep as before, but still pretty steep. We're heating up the liquid water until we get to point D, and point D at 100 degrees C, that's the boiling point of water. Well, now, before that water starts to boil off, it's going to take heat until we get all the water to 100 degrees, and then we get to point E, and then now we start to see the production of steam. Okay, so the key thing here is when we want to figure out energy calculations, we'll have a component to get us from one temperature to another. Then we'll have a component of getting everything ready for that next phase, is how I think of it. Then we have another component heating it up to that next temperature, another component once again at that phase, and so on. So when you do those calculations, and we'll see some examples here in a little bit, it's kind of a multi-step calculation. And so I don't know if you necessarily need to draw out a diagram like this every time you do one of these, but you do need to kind of think about the process in your head a little bit. And once again, it's that temperature change, then what's the physicalness going on, then another temperature change, physicalness going on. And so for the phase change, it's the product of mass or moles of heat and heat of fusion or heat of vaporization, depending upon what you do. So depending upon which thing you're doing, you have a different constant that you'll use. And we'll see the differences here in a moment. Any questions on this? So let's take a look at a couple of homework problems then. Let's see. And just a reminder that even though we go over a few homework problems in class, all the homework problems answers are posted if you want to take a look at them later, or if you get stuck. You also can send me questions. I'm more than happy to try and answer any questions you have. Okay, so we have these two diagrams. At the top, we have the one that looks like a little ball sitting on something, and then one that's a little more flattened out. And so the question is, liquids can interact with flat surfaces just as they can with capillary tubes. The cohesive forces within the liquid can be stronger or weaker than the adhesive forces between liquid and surface. So in which of these diagrams do adhesive forces between surface and liquid exceed the cohesive forces within the liquid? What do you think? If the forces are stronger within the liquid, which one of those would it be? The round one or the flatter one? It'd be the rounder one, right? Because if the forces are really strong within the liquid, then everybody's still kind of hanging out together, all the molecules. If the adhesive forces are stronger, so in other words, if there's a greater attraction between the material that's in the liquid and the surface, then it's going to kind of flatten out a little bit. In which of these diagrams, what happens when water, well, let me just ask it this way. So one of those is, so first of all, is water polar or non-polar? Polar, right. And so if water is sitting on a polar surface, what do you think is going to happen? It'll flatten out. That's our like dissolves like type thing. We have opposites attract and like dissolves like. Those are two things you should go to your grave remembering. So then if water's polar, if it's a polar surface, it'll have attraction. If it's a non-polar surface, then what will the water do? It'll be that beaded up look, right? And so if you have a raincoat, do you think that material on the outside of the raincoat is polar or non-polar? Non-polar, right. If it's polar, the water will just soak in. Like dissolves like. If it's non-polar, then it'll bead up and hopefully roll off you and you don't get all wet. So I think it's supposed to rain today, so hopefully you have a non-polar jacket with you. Okay. 1139, let's look at that one. And in that one, name the phase transition of each of the following situations and indicate whether it's exothermic or endothermic. Okay, ice is heated and turns to water. What process is that?
Endothermic.
It's endothermic, and that's melting, right? So if you're melting something, you got to put some energy into it. Wet clothes, drying on a summer day. This means you're hanging it outside on a clothesline. None of you probably know what a clothesline is anymore, but used to be people would hang their clothes outside and let the water evaporate. So that's evaporation or vaporization. So that's going liquid into gas. So an endothermic process. Frost on a window, what's happening there? Well, it's a deposition, right? You have atmospheric moisture, gas phase moisture, and now suddenly it's a solid. So you're going from vapor to solid. Depositions, we said, going from there, where it's a gas, down all the way to a solid, we said that's an exothermic, rather. And then the last one, water droplets on a cold glass. In this case, they're seeing lemonade, but you have a cold glass, you got ice in it, it's real cold, you see the condensation on the outside. What that's doing is it's taking the water that's in the atmosphere and it's condensing that water on the side of the glass. So you have it going from a vapor phase to a liquid. So that condensation, we said going from vapor to liquid, exothermic, right? Any questions about those? So one thing I like about that example is we talked before about why do you care about these heat flow changes and just all that stuff going on? And yeah, you know, doing the calculations, you may not be that concerned about as time goes on, but just kind of understanding what's going on in terms of all these. These are all things that we pretty much see every day. And so it gives you a feel for just kind of what's going on in terms of the chemistry behind it. and gives you a little better understanding. Okay, now let's do some math. So this is number 1145. And in this case, we're talking about ethanol. So C2H5OH is ethanol. We're told that it melts at minus 114 degrees C. It boils at 78 degrees C. It tells us the enthalpy of fusion, so that would be delta H, usually have a little F on it for fusion, is 5.02 kilojoules per mole. Its enthalpy of vaporization, so it's delta H with a little v, is 38.56 kilojoules per mole. It also tells us the specific heats of solid ethanol and liquid ethanol. So solid is 0.97 grams Kelvin, and liquid is 2.3 joules grams Kelvin. So that's kind of like our background information that we're going to need to solve this problem. And then what they're asking us for in particular are, so how much heat is required to convert 42 grams of ethanol at 35 degrees C to the vapor phase at 78 degrees C. So let's just go back here for a second to our curve. Okay, so what we're saying is we're starting at 35 degrees C, and we want to go to the vapor phase. At 35 degrees C, what state is the ethanol in? It's a liquid, right? So we're talking about, on our plot here, going from this BC area up to D, and then finally going up to F, okay? So this is where I was saying, you don't have to draw this out every time, but you can kind of think about it in this terms a little bit. So if we go then to the math of it, the first thing we're going to do is we're going to calculate what that temperature change is. So we're at 35 and we're going to 78. That's a 43-degree temperature change. So we're going to need that information. We're also going to calculate the molecular weight of ethanol. And that's what we're doing here with this value where we get 46 as the answer, okay? Why are we doing that? Well, we know that at some point we're gonna have to do something in moles. How do I know that? Well, one tip-off is if I look at my enthalpy of vaporization, enthalpy of fusion, what are the units on that? The units are kilojoules per mole. So a lot of times you can get tip-offs on what you're going to need just by looking at the units of the constants that were given, okay? And this goes back to what we talked about a lot last semester, dimensional analysis, okay? By understanding the units and what units we have to cancel out, even if you're kind of stuck, sometimes you can piece together what you need to do just by canceling the units out appropriately. So, okay, so let's do the first one. So we had 42 grams of ethanol, and we were told that the specific heat for the liquid is 2.31 joules grams Kelvin. Okay, so in that case, using this constant, we see that we're going to want a joules or kilojoules value. What's the difference between joules and kilojoules? Anybody remember that?
1,000.
Yeah, it's 10 to the third. Yeah. So 1,000 joules equals 1 kilojoule. So joules is a unit for heat, right? We've talked about that, delta H a lot of times. Heat flow, joules is one of the common heat units. So we've got grams and Kelvin in the denominator here. We had 42 grams. If we multiply that by 2.31, our grams cancel. Now we're joules Kelvin. We earlier had said our difference in temperature was 43 degrees. Whether it's Kelvin or centigrade, it doesn't matter when it's a difference. The difference is the difference. So that's a 43K difference. And then if we do the math, we would get 4.17 times 10 to the third joules. I've chosen to express it as kilojoules just because that's a little more normal to express this stuff. And so that tells us what it requires to heat the liquid from 35 to 78 degrees C. Okay, the other tip I'll give you on this is when we're heating that liquid, and I'm going to go back to this plot again. When we're heating this liquid, we're having a temperature change. We said when we're doing these things where we're not changing anything, there's no temperature change, right? So the temperature change tells us that this is where we're going to be. And so that's how we know which of those constants to use. Because the other one, the delta H vaporization, fusion, they don't have a temperature component in that. So we wouldn't be canceling any units out. So if you kind of forget which one you're supposed to use, once again, you could look at the units and say, well, in this part of the process, I have a temperature change and I have to account for that. The other thing is the amount of, when we think of heating something up, mass is important because the more you got of something, the more heat you're going to have to put in. So we've done this first calculation here, which tells us what the energy is to go from 35 to 78 degrees. Now, the next one is we're at that 78 degrees, and we said we got to get everything to that temperature before we start vaporizing. So now we're going to do that calculation there. And so here, we vaporize that liquid at 78 degrees. We use our other constant, our delta H of vaporization. So we have 42 grams. We need to change that into moles because our constant is kilojoules per mole. So we're going to use our molecular weight that we've calculated. That's that 46 value to change the grams to moles, and then multiply that times the 38.56 kilojoules per mole. So what we get is we get this first value here at 4.17, and then we get 35.2. We add those together to get our total energy value. So we had a couple steps to do. Any questions on that? Okay, let's look at B. Here we're going to take that same amount and we're going to convert from minus 155 to 78 to the vapor phase at 78 degrees C. We have all those same constants that we had before. So that hasn't changed, all that background information we were given. If we calculate our delta T, that's 41. And so now, first thing we're going to do is we're going to calculate heating the liquid to minus 114. So we have the 42 grams, we have our constant of 0.97 joules, grams, Kelvin, and then 41K, and we get 1.7 kilojoules. Then we need to melt the solid. So we've gotten it up to the temperature we wanted, now we got to melt it. So here we're going to convert the 42 grams into moles, And then we're going to use that second constant, 5.02 kilojoules per mole. Now we've gotten our second heat calculation. Remember, we're going through that stepwise process, like on that kind of chart, step chart that we had. Now we need to heat the liquid up to 78 degrees. So in that case, our delta T is 192. We have 192, we have using 2.31 joules. Grams Kelvin is the constant for this transition, and we get a value of 19 kilojoules. So now finally we need to vaporize that liquid, a similar process of where grams to moles, so that we can work with that constant and get a value of 35 kilojoules. So in this case, we had 4 different processes we need to do a heat calculation for, and then we'll add them up and get a total value of 60 kilojoules. So I would strongly suggest that you do a couple of these practice problems so you get comfortable with calculating those transitions. I guarantee you something like this will be on the quiz, okay? And so get to where you understand that kind of progression of steps as you go from one temperature to another, one phase to another. Get to where you are comfortable knowing which constant to use at which step. You know, the best thing is to just understand what's going on and pick the right constant. As I said before, if you get a little confused by that, the units a lot of times can bail you out. Okay, and just by doing dimensional analysis, it helps bail you out a little bit to understand. So, but the best thing to do is to practice a little bit and get comfortable with it. Okay, any questions about these types of calculations? Okay, we're going to move on to vapor pressure then. So when you have liquid molecules, there's some of them that always have enough energy to get to the surface and then escape the solution, okay? And so when they escape the surface, then they become a gas. As you increase the temperature of it, more of this happens. And so what we have here is a plot showing us that if the x-axis is kinetic energy and the y-axis is the number of molecules, and we're saying this dotted line is the minimum amount of kinetic energy needed for a molecule to escape. So in other words, putting energy in, putting heat in to get it to leave the group, so to speak. The blue plot shows what that distribution of molecules looks like in terms of kinetic energy distribution. And we see that just a small fraction of them have enough kinetic energy to break away from the pack. As you increase that temperature, which is the red plot, we see that that number increases. And so when we talk about vapor pressure, okay, what we're really talking about is how many of those molecules escape and kind of go out into the atmosphere. And as more of those molecules escape, then the pressure they exert increases. And that's where the term vapor pressure comes from. If you do an experiment like the one outlined on the slide, they have some ethanol above, they have an evacuated container below, they drip in some of the ethanol rather, and then they close it up. And what you'll see is in that closed system, you'll eventually reach an equilibrium where a certain amount of molecules will have that kinetic energy that we saw previously high enough so that they can go into the vapor phase. And then you have the molecules that are in the solution. Well, equilibrium means they're kind of going back and forth. As some go up, some go down, back into solution and back and forth. And in a closed system like this, at some point, you'll reach that equilibrium. And so the concentration above won't change, the concentration below won't change. There'll just be this constant exchange of molecules. That would be how you'd measure the vapor pressure, and that would be the vapor pressure. So you say, who cares? I don't do anything in an evacuated cylinder or anything like that. But what vapor pressure really tells us is it tells us how volatile something is. So liquids that evaporate easily, we say those are volatile. And what volatility means is they have a high vapor pressure. So you think about, we said vapor pressure was the number of those molecules that are in the gas phase above that liquid. When it reaches equilibrium, the more of those that are up there, then that's telling us it's going to have a higher vapor pressure. And by association with that term, it tells us that those are the things that are volatile. So what's something that's volatile? Okay, the one that always comes to mind for me is acetone. So acetone, a lot of times you use that in the lab. Some of the fingernail polish remover is acetone. If you spill acetone, no one ever has to wipe up acetone. You spill it, and by the time you go get a paper towel or something and come back, it's gone. Why is that? Because it's very volatile, has a very high vapor pressure. So in other words, those molecules sitting out on that table that you just spilled on, it'll be gone before you know it. It's gone into the air, it's volatilized. You know, you go buy gasoline, and a lot of times if someone has spilled some gas, you can smell it, right? Once again, that gasoline falls on the ground, spills on the ground. It doesn't just sit there forever. It's starting to volatilize, and that's what you're smelling. Anything you can smell is volatile. Anything you can smell has high vapor pressure. Okay, it's interesting because under certain situations, something can be considered to have low vapor pressure, low volatility, and it may not, and you think, oh, it's fine, but it really gets down to other properties. Some things at a low level can cause a problem. Some things have to be at a higher level to cause a problem. With the gas station or the acetone example, you spill a little of that, you're probably not too worried about it. There's other things, if there was a little bit spilled, you would be in much more of a panic. Hydrogen cyanide is one that is very toxic at low levels and has like an almond smell. And so if you're ever in a lab working with it and you smell almonds, you're probably going to be dead by the time you can tell anyone. So that's an example of where something very small amount could be a problem. So vapor pressure going with volatility is a big deal. What's another reason why you would want to know if something's volatile or not? Any thoughts on that? I'm going to pick on AJ. So you come to a crash. Do you want to know if there's volatile stuff in the air? Yeah. So if you show up and there's been a car accident and you can smell a lot of chemical smells, gasoline, whatever, you're probably going to operate a little differently than if you don't, I would assume. And so volatility is real important. If you have any gas appliances at home and you say, oh, I smell gas. Well, you don't. You can't smell natural gas. It doesn't have any odor. So they put stuff in it that you can smell at a real low level. And that's the reason, is it's real volatile, it has a strong odor, and you smell that little bit and it alerts you that there might be a problem. So volatility is pretty important, and that's associated to the vapor pressure. Let's talk about volatility and boiling point a little bit. So the boiling point of a liquid is the temperature at which its vapor pressure equals atmospheric pressure. There's also another definition called normal boiling point, and that's the temperature at which its vapor pressure is 760 torr or 1 atmosphere. 1 atmosphere, 760 torr, is considered kind of normal atmospheric pressure, but depending upon altitude, that number does change, okay? And that's why if you're up in the mountains, water boils at a lower temperature because that atmospheric vapor pressure is a lower value than this 760 torr or 1 atmosphere. Let's talk about something called supercritical fluids. So gases liquefy when pressure is applied. Okay, so if you have a gas and you put enough pressure on it, you can actually make it into a liquid. The temperature at which, beyond which a gas cannot be compressed is called the critical temperature. And then the pressure needed to compress the liquid at critical temperature is called critical pressure. And then the state beyond this temperature is called supercritical fluid. So we'd said all along we have solids, liquids, and gases. That's all we have. Those are our 3 states. Well, that's not exactly true. There's something called supercritical fluids. And we'll see a diagram in a bit, which kind of shows you the transitions between these phases. And I think it'll be a little more clear then. This is a list of some common chemicals that are used to form supercritical fluids. The one I want to point out is carbon dioxide, CO2. That's probably, if I had to guess, the most common supercritical fluid that's used on an industrial scale. So does anyone know there's a particular use for supercritical CO2 that's been used for years and years, and it's fairly popular, and it's something that probably a lot of you maybe have used before. Anyone have any idea what that is? I don't remember if I put it on the slide or not. I don't think I did. So supercritical CO2 is one of the ways that they make decaffeinated coffee or decaffeinated tea. So they do a supercritical fluid extraction, and that allows them to remove the caffeine out of coffee or tea. There's other ways to do it too, but a lot of people like this way because carbon dioxide isn't a hazardous chemical. The other ways to do it usually involve like an organic solvent to remove it. And so this is considered to be a little cleaner, a little greener way to do it. So phase diagram is the graph that we draw, which shows us for a compound the different transition states in terms of pressure and temperature. And so it shows us for that material what phase it's going to be at a particular temperature pressure combination. And it also shows us those points at which we move into that supercritical fluid phase. So a couple things is you'll see on this is our triple point and critical point. And at temperatures and pressures beyond the critical point, the liquid and gas phases are indistinguishable, and that's where we get a supercritical fluid. The triple point is kind of like what it sounds. It's where all 3 phases are in equilibrium. So let's take a look at one of these plots here. So what you have is you have pressure on the y-axis, you have temperature on the x-axis, and by kind of the colors here and then the lines, it shows us what phase, solid, liquid, gas, or supercritical fluid we're in. And so if we kind of look down here at the lower left here, we see this green line here, okay, kind of curving up till it gets to that T. That T is the triple point. That T is where solid, gas, liquid, everything is in equilibrium here. They don't have a scale on here. We don't have a scale here on this slide, but we have one on, I think, coming up, and we can see some actual values for this. So down here, around the sublimation deposition wording with those arrows, is telling us at that lower pressure, that lower temperature, we can only have either solid or gas. We can't have a liquid for this material, whatever this is. I'm not certain what this is. As we increase the pressure and we get above that triple point, well, now we see we could have solid, we could have liquid, we could have gas, just depending upon the temperature. So if I held my pressure, say I held my pressure at about where the P is on the left-hand side there, and then I come across and I increase temperature, I'd be solid, solid, then I'd come over to liquid, then I'd come over to gas, and I keep increasing. If I increase that pressure up, say to the E on the pressure and come across, I see I'd have solid, then I'd have liquid, and then I would never have gas. I would go to a supercritical fluid. And so that's what these diagrams tell us. It tells us for temperature, pressure type of combinations, what phase is our material going to be? And it also tells us, like I was saying on this last one, if we set our pressure up above this E on the y-axis and went across, and I kept increasing my temperature thinking at some point I'm going to get a gas, it would never work, right? Because it would go from solid to liquid to supercritical fluid. Any questions about the phase diagram? Okay. Here is the phase diagram for water. And so let's just take a look at that for a moment, because it actually has a scale to it in terms of temperature and pressure. And so a couple things I want to point out to you is the triple point for water. Now remember, what's the triple point again?
Equilibrium.
Right, very good. Equilibrium between the three phases, solid, liquid, gas. So that means you got a little bit of each there, right? They're all kind of going back and forth. That triple point is 0.0098 degrees C and 0.00603 atmospheres. So pretty low temperature, almost freezing, and definitely really low pressure, right? Not something we're ever going to encounter normally. The critical point, what was the critical point again? What happens up there? It does, yeah. That's where no longer is it a liquid or a gas, it's now this supercritical fluid, okay? And so in this case, that critical point is 374.4 degrees C and 217.7 atmospheres. Once again, pretty high temperature, pretty high pressure, okay? Not something you're gonna come across anytime soon, unless you're specifically doing something to do that. But what this tells us is, if we drop the pressure low enough, okay, these are atmospheres, is the units of the pressure here. And 1 atmosphere would be that 760 torr. So this would be kind of like normal room pressure, right? But if we could push that pressure down 10 to the minus third, for instance, and go across, we see we would never get a liquid. We would go directly from the solid to the gas, okay? All right, I think I mentioned that carbon dioxide, CO2, is often used to like decaffeinate coffee and do that extraction and stuff. And so if I wanted to do a supercritical fluid extraction using CO2, what would my pressure have to be at least? Anybody have a guess on that? How would I use this diagram to figure out what pressure might be useful? What pressure and temperature combination might be useful to do that extraction? Because if I'm doing an extraction, that means supercritical fluid CO2 is my solvent, right? So if I wanted to produce supercritical CO2, give me an estimate of what you think a temperature pressure combination would be that would accomplish that. Anybody on Zoom know?
Anything greater than 31.1 to 73 atmospheres.
Right, this is our critical point. It's telling us our critical point is 31.1 degrees C and 73 atmospheres. Okay, so this is 73 atmospheres here and 31 degrees. So if my temperature is higher than this, okay, that pushes me over here. And then my pressure, if I increase the pressure a little bit, it puts me up here and I'm above this area. So now I'm in supercritical land. I don't know what conditions they actually use, but what that tells me though is I could probably go to 35 degrees C and I'd be okay. 35 degrees C isn't that hot, you know? And so temperature wise, it works well. 73 atmospheres, that's pressurized, but it's not crazy pressure. And so that's another reason for why this would be a good thing to use to do that supercritical fluid extraction. You don't have to get to crazy temperature and pressure conditions. Remember what we said about water? Its critical point, 374 degrees C, 217 atmospheres. Which would you rather work with? 300 degrees and over 200 atmospheres, or 30 something degrees and less than 100 atmospheres? I know which one I'd pick. And you combine that with carbon dioxide is pretty non-hazardous. And so that's one reason why it's a good choice for those extractions. Okay, next thing, any questions about the supercritical fluids and the phase diagram? Okay, let's talk about liquid crystals. Has anyone in here ever purchased something that had a liquid crystal in it? Or do you not know, or you say, no, I don't like liquid crystals, or? Okay, so I have a cheap digital watch, relatively cheap. That displays a liquid crystal. A lot of the computer monitors are liquid crystal, things like that. So I guarantee you, your phone probably has liquid crystals in it, the display. All that stuff is liquid crystal based. And so what we're gonna do is we're gonna talk about what we mean by liquid crystals here. So some substances don't go directly from the solid state to the liquid state. Great, just what we needed, an exception to the rule, right? We just got through figuring out how to do calculations and understanding phase changes. Now we're being told, well, that doesn't always work that way. And so a lot of this got discovered back when people, years and years ago, when people were studying cholesterol. Cholesterol is one thing that has like liquid crystal properties. And so a lot of this came out of that. And so this is like a cholesterol type compound here that they're using as the example. And so in my experience, seeing liquid crystal, things that are defined as liquid crystals, they tend to be like a milky looking thing. And that's kind of the picture you're seeing here. It is that. And so there's some particular definitions of why something's a liquid crystal versus not, and all that. We're not going to get into that. But really, what we're saying is that liquid crystals are substances that go from solid to liquid, but not directly. They have this intermediate state, which tends to be this milky looking thing. Okay, not everything does it, only certain compounds do, and we'll talk a little bit about what it means when it does that. And the key thing here is for compounds to form liquid crystals, they have to have a way to order, and by order I mean physical arrange the molecules in certain ways, and there's definitions of those. So it's that ordered thing that defines whether it's a liquid crystal or not. So here's some of those definitions for the different types of things. So liquid crystals often are composed of rod-shaped molecules that are somewhat rigid, okay? They're randomly oriented in the liquid phase. So in the liquid phase, you have these, think of these kind of cigar-shaped molecules, and they're just all kind of jumbled up. In the liquid crystal phase, they start to get order to them. So there's patterns of where, if you look at them, you can see that they're no longer random. There's something called symmetric A and symmetric C liquid crystals, and these are ordered in 2 dimensions. They're ordered along the long axis, so the long axis of that cigar-shaped molecule, and they're in layers. And we'll see a little cartoon of this in a moment, which I think makes this a little clearer. The cholesteric liquid crystals, pneumatic-like crystals, those are layered at angles to each other. And so from one layer to the next, orientation of the molecules rotates by a fixed angle, and so it's kind of like a spiral. It's much easier, so these are definitions you should know, but it's much easier to see these pictures. And this, I think, gives you a better feel for what we're talking about. So starting over on the left here, we see our cigar-shaped molecules, and when it's in the liquid phase, you see they're all kind of jumbled. They're just all kind of arranged haphazardly. Pneumatic liquid crystalline phase, that's where the long axis of the molecule, so in other words, the long axis of the molecule is aligned, but the ends are not aligned. So in that pneumatic, if they're a pneumatic type, they're all, say, pointing up, okay? But that's the only order. They're just oriented. So we've gone from pointing up, pointing to the side, whatever, to everything pointing up. Somatic A, they're aligned by the long axis, and then they start to have planes that are perpendicular to each other, okay? So once again, we see a little bit more order. The next one, somatic C, we still have that alignment along the long plane. We have layers, as we did with somatic A, but now we start to have a little bit of an angle to it, a little bit of a tilt to it. Okay, and then finally, the cholesteric crystalline, now we have layers, and we have layers where the layer itself is all aligned up in some fashion, lengthwise, and also we've got layers there, but then the next layer down, it's a little different, and then we get back to the other. So starting from liquid phase, all the way across to the cholesteric liquid crystalline phase, we get order, increasing order. When you talk about these things being used in displays, there's things you can do. Sometimes it's putting a little electric field, sometimes other things you can do to make these things move, okay? And that's where some of the properties come into of using them in the displays and things like that. But it's this semi-solid type, milky type phase that really, if you look at it closely, has order to it. And like I said, depending upon the compound and some other things, how much order it has and what type of order, that's what's going on in the liquid crystals. Okay, so there's a few homework problems. Let's see. What I'd like to do is, let's look at this phase diagram. And then we'll end for today, 1161. So in this phase diagram, this is the phase diagram for neon up here. The first question is, what's the melting point? Approximately. So we said 1 atmosphere is roughly atmospheric pressure. So if we go over, and this is where the people on Zoom are really missing out on the good part here, because I'm looking at the board. 1 atmosphere, we go over, and we see that's, I don't know, 25 degrees maybe, roughly. This is in Kelvin. So that's how we would pick that out. The next question is, over what pressure range will solid neon sublime? First of all, what does sublime mean? Go solid to gas, right? So what pressure range could I get subliming? Well, I look at my phase diagram and say it's got to be below the triple point. That triple point, I don't know, what is that, about 0.7, 0.5, something like that atmospheres. So if everything from here down, if I keep the pressure from here down, so I could draw a line across there, I could then increase the temperature of any of those, and I could get it to go from solid to gas. And then at room temperature, 25 degrees C, can you liquefy so if you're at 25 degrees C, which I guess is about here, can you liquefy it? So 25, okay, I'm sorry, 25C would be way out here, because this is Kelvin. So think of my temperature, this 25C is 298 Kelvin, so I'm way out here. Can I liquefy it? If I keep increasing that pressure, can I liquefy it? Let's just say I'm at 100 Kelvin. Is it possible for me to form liquid? No, because if I increase that, it's going to become a supercritical fluid, right? Because I'm past that critical point, the temperature out there. Okay, any questions about anything we covered today? All right, next week we'll pick up with chapter 12 then. Thank you.